Okay, 3217 draws an interesting looking circuit. Here we have a 24-volt battery, and we go to a switch with little curved parts on it. It's kind of like this. Here's position A, and here's position B, and here is the switch. Comes over here. Strange looking switch. So this is 24 volts. And basically what the switch is doing is, because of these curved parts, it's telling you that you're always touching one or the other. And if we just didn't have the curved parts, you might think when you go from A to B, you have to have some time where it's touching neither side in the middle. So here with these symbols, they mean the switch is always touching A or B. It's never touching either one or the other. Okay. And that's really important just for helping us do the problems correctly. Then there's an inductor here of L equals 5 millihenries. And then it comes down to a resistor, a branch actually of 2 resistors, and it comes back together, and then that makes it back over there. This resistor is 450 ohms, and this one is unknown, is R. And that's all we need to know. So the first question is, what is R if the time constant is 15 microseconds? So what you really, the only trick to this is that we have basically an LR circuit. We can apply 12 volts EMF to an L and an R, and this branch together makes an R effective. So you remember adding resistors in series and parallel. So we have an effective LR circuit. The time constant, we said, we want it to be 15 microseconds, so 15 times 10 to the minus 6 seconds equals L over R. L is 5 millihenries, so 5 times 10 to the minus 3. And R is this REFF. So you have to solve for REFF, the effective resistance, and then get this one, because you know that one. So you can do it all in one step, you can do it in 2 steps, whatever you want to do. Here, I'm just going to do it in 2 steps. Let's get the intermediate resistance just to make it a little easier. You bring this here, that there, 5 over 15 is 0.333, 10 to the minus 6 over, coming up over 10 to the minus 3 gives you 333. So it's 333, actually 0.33 bar. So 333.333. That's the effective resistance, but we actually were asked for this one. So we just keep in mind that the way you add resistors in series is something like this: 1 over the effective resistance is 1 over R we're looking for, plus 1 over 450, 2 that are in parallel. And then you just do the math on that, and you get 1.29 kilo ohms. If you cut this off and just make it 333, you get 1.28. But whatever, you get 1.29 kilo ohms for R. And that's the answer to part A. So the question was simply, what is R if this is 15 microseconds? Part B says, when we now throw the switch from A to B, what is the current in the inductor? So the switch goes from A to B. What is IL at the moment you throw it? So they don't explicitly say it here, but what they're implying is it sat in A for a long time. Okay? You can imagine if the time constant is 15 microseconds, if it sat there for as much as 1 millisecond, that this thing is going to reach steady state. That in that plot that we thought about, where you're looking at how does the current change versus time, right, and it gets up to some value. This. What it's telling us is this time constant to do this is on the order of 15 microseconds. So if you wait a second, you're way over here. What that means is your current is saturated, it's not changing. So you get no EMF drop here. So at the instant that you throw it, if it's all steady state, right when you throw it, the current, let's think in terms of potential. The potential would be 24 volts here, and since you've made it to steady state, There's no changing current, there's no EMF here. You basically have 24 volts here. All your voltage drop is across the resistors. When you throw it to B, what happens? Now we have an EMF across here and the current will flow back. And then the changing current will create an EMF in the inductor. Complicated stuff happens. But the instant you throw it, you just have 24 volts here, 0 volts here, and your current is whatever was going through this little resistor network. Okay. So to do it, then you can just ignore the inductor, and basically you just figure out it's 24 volts over the effective resistance current. Then we're trying to get is 24 volts over 333, which is 70. I can't tell if that's a 72 milliamps. And that's the right answer, 72 milliamps. So we didn't have to use the inductor to get the current for part B, but we did use it originally to get the effective resistance.